All right, join me for the Math on the Spot video. Get scratch paper if you don't already have some so you can follow along. All right, here we go.
Oh, come on, I want you to grow. I want you to grow. Oh, hi. I'm just working and doing some gardening, trying to get a really, really neat plant to grow. But we can worry about that a little bit later, because this whole plant business reminds me of a great riddle involving Yashi and his attempt to try to actually analyze some data about plant growth. Let's check it out together, see what we think. Okay, well, Yashi made the box plots here to show the data he collected on plant growth. Now, he thinks that the variation in the bean plant growth was about the same as the variation in the tomato plant growth. The question is, what do we think about Yashi's conclusion? So here's the bean plant growth in inches, and here's the tomato plant growth in inches, and he thinks that, in fact, the variation is the same. That's his little thinking at the moment, that the variation are about the same. So let's think about it together. So one way to look at the variation is to measure the range. So remember how to find the range. You just take the absolute largest value and the smallest value in your data set and subtract them, which is really visually in the box plot, just looking at this length right here, the length from the distance between the largest and the smallest. So let's do the bean plant first. So the bean plant growth, the range would be, well, 13 minus 3, which is 10 inches. What about the tomato plant growth? Well, let's take a look at the tomato plant growth. So with the tomato plant growth, we see a range of 13 minus 3. It's actually the same thing. So in fact, the range is the same. The range is the same. So therefore, he says, oh, therefore the variation is about the same. Well, that's true that the range is the same. There's no debate about that. But let's look a little bit deeper and think about variation. Let's look, for example, at the inner quartile range. Remember, those are the values that are at the second and third quartile. And those are kind of the ones that are, in some sense, in a way, clustered around the measure of center, which is right here, which is known as the mean. Well, let's take a look at the inner quartile range. That would be the distance or the length of this little rectangle, or the distance between this point here and that point right there. So what would it be? Well, this is about between 9 and 10, so that's about 9.5, and this is 8. So the difference, the inner quartile range, would be the difference between 9.5 and 8, and we see that is actually 1.5 inches. But what about down here? Well, just visually you can see that this is going to be a lot longer than this. It's visually apparent. And so it tells us that there's more variation here, right? This is longer. This is tighter. All the data is tight. Here the data is spread more. And if we look at the actual interquartile range, we see it would be 11 minus 6. And so here we see 11 minus 6. So while the range in both data sets, in fact, is the same, their interquartile range here, 11 minus 6 is 5. We see that here the spread is 5 inches, here the spread is only 1.5 inches. The data is much more tightly packed in that second and third interquartiles, and so therefore, actually, we can see a difference. And so I think that even though he says the variation is about the same, I don't think so. This has less variation, and this has more variation. And so here's what I would think. I would think that the interquartile ranges show that there's more variability. There's more variability within the tomato plant than within the bean plant growth data. And so I think that actually Yashi's conclusion is not perfect. Although I have to admit that the ranges, in fact, are the same, but if you look at the interquartile ranges, we see actually substantial difference. That this rectangle is more narrow, or is tighter together than this one, and so here there's more variability in the data. So that's a great way of actually seeing data in a richer way by taking a look at the variability. And the more variability there is in the data, it means that the more spread out it is. And the less variability means that they're all tight together. So anyway, whether you're looking at variability or ranges or just trying to understand data, we can see that kind of information grow out naturally just by thinking about statistics. And in fact, this reminds me, it gets me back to my plant, because remember, I was trying to actually get this plant to grow myself. Here we've got these bean plants and tomato plants all growing nicely, and here I can't get my plant. Let me see if I just add a little bit of, oh, wait a minute. Oh, I think it wants to grow now. Oh, here it goes. Oh, here it goes. Look at it. Yeah. Oh, my goodness. Look how big. Oh, it's big and strong. It's big and strong. And now it's waving goodbye. Have fun thinking about math and statistics, and we'll see you soon. Oh, yes. Just working and doing some gardening.
Thanks for watching, and I'll see you on the next one.